All right, hello NRF. So I am back in my classroom actually, and hopefully this will go okay. It's not quite as, I like my setup a little bit better at home, but this is I think the best that I can manage here right now. So we have one more new topic, and that's going to be this one. And then next week I think I'm just going to give you some stuff that you can review on your own time, and that'll be the end. So we've made it to the summertime, and I hope that you followed along with some of it, and it will help keep you feeling relatively prepared for your grade 11 courses next year. So we were in the middle of doing solving systems of linear equations last week. So the idea here is that when we are solving systems of linear equations, we are going to have, since they're linear equations, they have two variables. So we can think of that as just being like y and x. Could be different letters, but typically y and x are what we use most of the time. And we have two equations going on at the same time. Now, the way that that works is that you can take those two equations and you can solve them a number of different ways. So last week we did graphing and elimination. So graphing is when you take both the equations and you place them on a graph, I guess obviously. But when you do that, you have one of three situations happen. Actually, for any one of these, you have one of three situations happening. You could have what is over on the left-hand side there, where you have two lines that are intersecting each other at a single point. That single point is the only solution to that system of equations, and so that point has an x value and a y value. So the solution to the system is the point, and in this case, if I can read that on there, it would be at 2, 1. So we'd have a single solution there at 2, 1. For this one, this is an infinite number of solutions for this middle one. The idea there is that they are actually the same line. Whether we could tell that or not initially is not important. It may be that one's written in slope point form, one's written in slope intercept form, or maybe there's general and standard form too, or forms. There's all kinds of different ways and non-standard forms that you could write the equation of a line. When all said and done though, sometimes you can get two things that look different, but they actually are the same linear function. So if that's the case, then every single point on that line is a solution. All of them together are the set of solutions. So that's what's going on here in the middle. And then lastly, we have two parallel lines, and two parallel lines never are going to meet each other at any particular value. So they actually have no solutions. So the options are basically one solution, infinitely many solutions, or no solutions. That's true whether you do it graphically, which kind of the setup that we have right here is that we're looking at them graphically, and that's great. We did them last week by using elimination, and elimination was the idea that if you have two of these equations going on at once, you can take one of the equations and subtract it or add it to the other. You can also multiply your equations by any amount and then do the adding and subtracting. So sometimes you might multiply one equation by 2, for instance. You might multiply 1 by 2 and 1 by 3 and do a subtraction. The goal of that subtraction or addition is to eliminate completely one of the variables when you create your new equation. So getting totally rid of x or totally rid of y. And if you want to take more of a look at that, it's the last video. And we are, though, going to concentrate instead on doing this in terms of this other method, which is substitution. So substitution it's got a lot of similarities because it's another algebraic process, just like elimination was. But instead of thinking of it as like equation 1 and equation 2, and you basically are going to take some multiple of one of the equations and add it or subtract it from the other, this time we are going to focus on solving for a particular chunk in one equation that we will completely replace in the other equation. This one is set up really nicely for this, and so it's a good first place to start. This is the same as the example from last video. So we should already, I say we already should know what the answer is. I can't remember what it is, but we'll come up with it here in just a moment. So if we take this y right here, it is actually already in the equations, the way that they're set up, it is solved for. And so what I mean by that is we have an isolated y all by itself on one side of an equals. Because we have that, we have another thing that y is equal to already very clearly laid out. Negative x plus 1 is the same thing as y. So that equal sign that appears between the y and the negative x plus 1, that's equivalence. So the two sides are the same thing for this particular question. So what that means is instead of writing y, I can, anytime I see that, write negative x plus 1 instead. Now, if I did it just in the second equation, it would give me kind of nonsense. So I would say something along the lines of negative x plus 1 is equal to negative x plus 1, and then that's not, it's always true. So it doesn't give you anything interesting. However, in my other equation up here, I want to know when this thing is going to be true at the same time the second part is true. What that allows us to do, or what we are going to do with that, is we can take the version of y that we have in our second equation and substitute it in to the position of y in the first equation. So I'm going to say that y, which is the same thing as negative x plus 1, minus 3 is equal to 2 onto x plus 2. So what we have done is we have done a substitution, so just taking the part of our first equation that is in one of the two variables and substituted the version of that from the second equation that has only y described in terms of x and other numbers. So what has happened is I've created an expression, or an equation I guess, down here that only has x's in it. There are no y's there at all. So what we can do with that is we can actually pick away at making this look a little bit nicer. I'll do it really slowly. So the bracket is useless. I probably didn't need the bracket there in the first place. I have a problem with over bracketing things. Just ignore me when I do that. But we'd also have distributive property thing going on here. So we'd have 2 times x and 2 times 2. So that's going to give me 2x plus 4. And now the goal is going to be to solve this, I guess, for x. So I'm going to move all my x's over to my left-hand side. It's going to make them negative. I'm not too worried about that. But I'll subtract 2x from my right, which means I'm going to subtract 2x from my left. I'm going to be left with negative 3x if I do this. Right now, if I put these two things together, it would be negative 2. So I'm going to add 2 to get rid of that, which means I add 2 to the other side as well. It's going to give me 6. Dividing both sides by negative 3, we're going to end up with x is equal to negative 2. So that is the x value that satisfies the second equation and the first equation at the same time. So what we can do with that is we can take that value of x, go back up to the original, so negative 2, and choose either one of these equations to put that into to solve for what y would be. My second equation is quite a bit nicer looking than the first in terms of complexity. So I'm going to just say y is equal to negative 2 plus 1, which means y would be equal to 3. So our end solution is when x is negative 2 and our y is positive 3. So that's our answer here. So substitution, again, is when you take, you rearrange one of your equations to completely replace that variable in the other equation. So again, I'm not taking some multiple of one equation and adding it or subtracting to the other. I'm taking a piece of an equation and putting it into the other one. And it does the same job. It gets you down to an equation that only has one variable left in it, which means you can solve it and get an answer. So we'll try that a couple more times here and see how it goes. This was from last week too, but if you get to the end of one of these and, for instance, when you do some substitution, you end up getting 0 is equal to 0. That means that there's an infinite amount of solutions. So that may come up from time to time, that you get something that's obviously true all of the time. So that's every possible solution is okay. If you get something that's nonsense and is never true, that means there are no solutions to that. And so that would be parallel lines, for instance. These would be the same line. And then the left-hand side, this is just a single point. And the single point is the x comma y value. So it's fairly intuitive, I guess, that that would be the case. Once you get down, you get a single x value and a single y value. All right, so in this particular case, neither of these is rearranged for either x or y. So we could do this with elimination. I could probably take, actually, do you know what? As a little bit of review, I'm going to do that right now. 3x plus 9x is 12x. Y plus negative y is 0y, so it just kind of goes away. And then 5 plus 15 is 20, and so we get x is equal to 20 over 12, or x is equal to 10. Oh, wow, I should just divide by 4, 5 over 3. All right, so that's great. And then I can put that back into, for instance, the first one there. And 5/3 put into this would be 3 times 5/3 plus y is equal to 5, which says 3 times 5/3 is just 5. Subtract 5 from both sides, and we end up getting a y of 0. So that is actually a really nice, tidy elimination problem. That's great, and I'm going to put down that answer, and we're going to compare it to doing it the substitution way. Sometimes one of them will seem better than the other. They're not always one better than the other necessarily. They have a little bit of a different feel to them, but you don't have to get too caught up in that. So I am going to take my first equation and I'm going to choose to rearrange it for y. The way that I do that, subtract 3x from the left, subtract 3x from the right, and it ends up being y is equal to 5 minus 3x. Now, once I have this, I have the equation rearranged for y. So I'm going to take that and I'm going to substitute it into, I said that kind of weird, substitute it into that y position in my second equation, which is going to allow me to write 9x minus, and then I have to do this, I'm not over bracketing this time, because what I want to do is subtract y. Y is the entire expression, 5 minus 3x. So I'm subtracting the 5, but I'm also subtracting the negative 3x. So that's going to affect the sign on the negative 3x, and it's going to turn it into an adding 3x actually in the end. So this is, I'm in the middle of doing this second equation rewritten. So 9 times x minus y, the new way that we write y, is equal to 15. So doing this, we get 9x plus 3x minus 5 is equal to 15, and so 12x is equal to 20, which look pretty familiar. X is equal to 5/3. Put it back up into the other one, and we would get that the y is equal to 0 like we already did. So I'm not going to actually think about putting it in, although we could just put it in right here and say 5 minus 3 times 5/3. Which is going to give you 0, and so you get your same point of 5/3 comma 0. All right, so you might feel like you prefer that method of elimination. You might prefer the method of substitution. I'd like you to be pretty comfortable with both of them. They're both good algebraic processes to get comfortable with, even if they do the same thing in this case. All right, so let's do one more, and that can be enough for now. So in this particular problem, you get 3x minus 4y is equal to 0, and 5x plus 4y is equal to 17. Now I'm going to show you a little bit of a trick. You can solve for just a single variable like y, and that's fine. But you can also solve for something that shows up in both of them. Now again, this would be an easy elimination, but that's okay. I'm going to take this and say, let's solve for 4y in my second equation. 4y in my second equation, if we solve for it, would be 17 minus 5x. So subtract 5x from the left, subtract 5x from the right. Great, this is my rearrangement. I'm going to take that 4y, and I'm just going to put it right up into the 4y position in my first equation, which gives me 3x minus, and then the entire 4y position there. And then that's going to be equal to 0 in that first equation. So we get 3x minus 5x, which is plus 5x, minus 17 is equal to 0, which means 8x is equal to 17. X is equal to 17 over 8. And that's a pretty icky fraction, but it's fine. And I'll show you graphically. We'll do this in Desmos in just a second, and we'll see if we can get that particular value. 17 eighths, 16 eighths would be 2, so that's 2 and 1/8. 1/8 is 1.25, so this is going to be 2.125 is the equivalent x value there. And if I put that back up into, they're both pretty icky. Eighths, gross. All right, so I'm going to put it into the this one here. So 17 eighths. So 17 times 5 would be 50, 85. So 85 eighths. Ooh. And then that would be 80 plus another 56, so 136, I think, eighths. Subtracting there, subtract 100, add 15, so 51 eighths. So 51 eighths, and then we'll divide by 4 on both sides. So it would be 51, 30 seconds. Whew, okay, so I'm going to say that the answer here is 17 eighths and 51 30 seconds. And so 51 30 seconds is 1.6 something, I think. We'll compare it here in just a second. So what I'm going to do is I'm going to come over to my computer here, and I am going to pop over onto the screen there in just a second Desmos. And Desmos is an online piece of graphing software. It's pretty useful for this sort of thing. And so I can't, my short-term memory is real good. So we have 3x minus 4y is equal to 0. So 3x minus 4y is equal to 0. And there is our nice line there. And 5x plus 4y is equal to 17. So 5x plus 4y is equal to 17. All right, so this has given us our single value solution here. So hopefully 2.125, oh, I'm clicking on the wrong screen. 2.125, that's good. And I said about 1.6, so that looks pretty good too, but I'm going to double check it because I want to make sure that that's okay. Actually, I'll double check it so that you can see it. I can use Desmos as a calculator too. So we're going to put in here, this is 51 30 seconds. So 51 divided by 32 is 1.59, and then rounds up to a 4, so that's good. If I were to zoom, whoops, sorry about that, zoom in a little more here, it might give me those same decimals for the 30 seconds. I need one more place value. Will you do it, Desmos? Will you do it for me? No. See how much time Mr. Reed can waste by zooming in on a point trying to get it to describe one more decimal value. Oh, that's so sad. It might not. Anyway, it's the same number, but it's rounding it to the 4 decimal places. All right, so this is the process of using substitution. Basically, you're going to rearrange one of your equations, normally for just the plain variable. However, in this last example, that's not what we did. We actually rearranged for 4y just because it was convenient. And we could take it and just substitute it into the position of the 4y in the other equation and come up with an equation that only has a single variable. So anytime you come across a linear system of linear equations, this is possible. So we could just I could make a very random linear equation question, and so if I just write some weird stuff here. So there are two equations. I didn't even put any thought process into making them. We could get some really ugly numbers. That's fine. Could get that there's no solution. Could get that there's an infinite many solutions. Won't be that one, but that's okay. So when I start one of these problems, what I typically do is if there is just an x or just a y, I solve for that because it's the simplest to replace, in my opinion. But we could do whatever we feel like. I am going to choose to solve this for x. So that would be x is equal to -2. We'll move the 4y over to the right-hand side, so it becomes -4y. Take that x and we'll put it into the first equation. So that's 2 times the other way that we write x, which is this thing over here, -2 minus 4y. And then -3y is equal to 5. So you'll notice that this time, I don't know, yeah, this time here, I replaced y and ended up solving for x. This time here, I replaced y and ended up solving for x. This time here, I'm replacing x and ending up solving for y. It actually doesn't matter which of the x or the y you solve for first. Either one of them is fine. All right, so we would get -4 minus 8y minus 3y is equal to 5. So that's minus 11y is equal to 9, or 11 is equal to -9 over 11. Or sorry, y is equal to -9 over 11. Again, that's not the prettiest value, but that's okay. Leave it in a fraction form. That's kind of the safest way to deal with that sort of thing. And then I'm going to take the last thing that I have written up there at the top, which says x is equal to, it's -2 minus 4 times -9 over 11. So in this case, we would get y is equal to -2 plus now, because it's going to be negative times a negative. 4 times 9 is 36 over 11. And then -2 is going to be -22 over 11 if I put it on a common denominator, plus 36 over 11, which gives me 14 over 11. So we would get -9 over 11, comma 14 over 11. And so we'll go throw that into Desmos. One last thing that we do there, and that can be good. So as another example. So let's let me go up to where I made some questions there. I should be able to see both at the same time. That's good. 2x minus 3y is equal to 5. Also, we had x plus 4y is equal to -2. So those are my, my two lines there. And hopefully, this value here ends up being what we were hoping for there, if I didn't make any mistakes. Oh, I gotta pull that down. Oh, I labeled it poorly. So one of the things I did was, I think when I was working on it, I had it as an X right here. You can kind of see it, but then I was like, oh, it's a Y, but it's not. It's an X. My apologies for that. Oops, sorry about that. So it's that is a value of X there. We'll fix that. So X, X, and so X is 14 over 11. So these are backwards. 14 over 11 and -9 over 11. Okay, so let's just double check that again. So 14 over 11 and -9 over 11. Oh, my memory is so good. I apparently deleted that, and need to find it one more time. -2. -2. So is 14 over 11, comma, -9 over 11, the point we're interested in? And the answer is yes. So solve for that correctly, other than my mislabeling of my x and y there at the end. But there we go. So it is at the right spot. So that is solving equations by using substitution instead of elimination or instead of graphically. So again, hope you're taking care, and we'll do a little bit of a review thing next week, but that is the last video in terms of new content. So wish you all the best. Take care.